Okay, hear me okay? Excellent. So, thanks for the introduction. Hard to follow Lou, to be honest. Great talk. We're going to talk about some of the challenges that we face deploying AI. Now, talk is focused on a um, detection system within manufacturing, and then the changes that we are anticipating given Gen AI and some of the challenges we faced as we deployed that solution. So very quickly, just about Seagate in Springtown, those of you not aware of us, we're established in '93, over 1,500 employees at the current site in the Northwest, and one of 6 plants globally with nanoscale precision manufacturing. A quarter of the read-write heads within the world are provided from our facility in Derry, and we've 30 years of experience in innovation and partnerships with the recent large investment from Invest in I think the largest they've had from an R&D perspective in their history. Very cool YouTube video there, just a hard drive if you want to look at our new product advances. And in particular, this new product has very high complexity, content, and then customer quality tolerances. So that for us drives a significant challenge from a data collection perspective and then the value we'd like to realize from that data. So the data reality within the semiconductor fabs, we've a wafer fab here in Springtown and one in Normandale in America. But those of you around long enough, the 3 big data Vs that you heard about 10, 15 years ago, of those 3 Vs, volume, velocity, and variety, we essentially are challenged with the variety. Volume and velocity can be solved through modern IT technology or infrastructure choices, but the variety problem here we try to solve with an algorithm. To sort of crystallize that variety that we face, we've got a schematic here on the left-hand side of our sensor of a vacuum process tool, and it's got 6 chambers. For those of you not familiar with semiconductor manufacturing, each one of those chambers performs a different process, and there's a transfer module with 2 robot arms in the center, and then there's some peripheral activity on 2, 3, and 6. And each one of those modules has between 50 and 200 sensors at any given time, sampling different hertz of rate. The data being generated from this is multimodal. You can see that it's a batch process. It's not continuous like a standard pump or process that's just meeting a set point. There's very specific regions that this need to be in, and there's certain features that we are interested in. Currently, we have over 1,000 pieces of unique equipment that are currently enabled for data collection, with so much more being brought online every time we make a capital purchase or advance a technology, plus retrofit our historical tool sets. And there's about 500 million samples of data per day that we have to try and process and analyze, with approximately over 17 million distinct control parameters at any given time. Given that, there is a significant challenge from our landscape where the data is highly dimensional. It's multimodal, as you've seen from the sensor traces, but the equipment is non-stationary. So much like your car or any other piece of mechanical equipment, it will need maintenance and it will be consumables. And as those consumables change, they will be weared, and it will change the set point and the distribution of that particular data set. Add on top of that already complex situation, there's an infinite fault scenario where you could fix all historical faults and still be a new one tomorrow, and that will continue forever given our dynamic environment. And we have very subjective labels or no labels at all of our space. There's other constraints from an engineering, data science perspective, consumption, or somebody else mentioned alert fatigue, very good way to put it, resistance in the culture, or a lack of awareness of the actual problem statement, and then data quality. We'll get on that in a second. So within this space, the complexity I've just described was developed over partnership with our engineering team, and this lesson 1 is poacher turned gamekeeper. So I've had the privilege of working in some of those equipment teams, and I'm familiar with the problem statement, but some of our other data science challenges, we have to work very closely with the engineering team and adopt those into the organization to ensure that we know the complexity. The current problem I'm going to go through essentially is the 3rd incarnation of that. So, too many sensors, process configurations, not enough resource to provide the coverage that we need to establish our product quality, and reducing the overall value extraction of that particular data set. AM KPIV, our autonomous monitoring of sensor data system, is a novelty detection capability for time series data. If you look on my LinkedIn and online, there's multiple papers published on this, so you want to get into more detail. The end state is that AM KPIV will be acting upon the equipment and our wafers or products in real time as we process them to catch deviations from the actual norm. So getting into the methodology and the factory deployment, this presentation was supposed to be nuts and bolts around what we've tried, what didn't work, and lessons along the way. So historically, Six Sigma statistical methods didn't work. Too many configurations, very manual in their setup. And then that creates another beast to maintain from the engineering teams. And although in some narrow fields they do work, they're not extensible in that non-stationary multimodal environment. Machine learning comes along, and that is a solution. However, the feature selection and engineering process reduces your domain, and that infinite fault scenario creeps up, and then you lose that particular area that you need to detect a fault in the future. So, what have we proposed? You know, we're talking about GenAI here today, and at the current scale that we're talking about, the GenAI may work, but at what cost? You know, to host it within our environment, it's very difficult. So this proposed solution, using a very vanilla convolutional autoencoder here, provides a way to learn our historical data in an unsupervised way. So this system essentially takes historical data, ones and twos on the screen here, very rudimentary, and learns what that is. So from our perspective, those process chambers you've seen at the very first schematic will show us these sensors are in this domain for the entire trace, the multimodal aspect, and then it'll learn the latent structure and it'll put the outputs out. So from a sensor perspective, at the moment in the time series space, you know, this type of solution isn't as extensible as other type image solutions or text type solutions as well. Once we then have that particular full reconstruction of the data, what we see then is areas of high error, and that error rate drives our engineers as well as our further AI systems to regions of importance in particular sensors or aspects of the data that are particularly important. And in this case, 4s and 9s. So this is just an example. As I say, online there's multiple more detail on this. On average, our models are 40 megabytes in size with 3.5 million trainable parameters. So on average, around 4 to 5 minutes to train. Very lightweight. They cover this domain. So this lesson here is faster horses, Mr. Ford. So, you know, this is the third iteration of this system, and as I mentioned before, statistical and both machine learning failed at trying to cover this domain. So with a research effort in partnership with Ulster University and other departments, we had to come up with a very radical solution in manufacturing, and this is novel in its space. Okay, so from an MLOps perspective, there's a lot of examples that were talked about today around, okay, we've got these examples and use cases, but then the models work on a proof of concept. What is required to host this type of model in a production environment that runs 24/7 in a semiconductor fab, both here and in an American site? There are 2 complete pipelines within this architecture, and my challenge to you is if there's any better way to do this, we've open ears. We're very much a novice in this particular space, and the choices we made might not be optimal, but it works. So, you know, from the training perspective, on the left-hand side, you'll see configuration and historical training database. We'll come on to the database in a second around the content of that. And the configuration management reduced the cost of ownership from our engineering resource. If you imagine the statistical approach, that would have been very unmanageable, all the individual parameters being maintained by the engineering teams. And then how do you change that if there's any shifts within new products or processes? That's practically impossible. So there's a process there that automates that and generates the configurations. Models are trained using a GPU or CPU, whatever's required, and then they're all stored within an artifact store, so offline training pipeline. And this is hosted in Kubernetes to be multiple pathed. On the inference side, we have our tool data layer, the TDL here on the right-hand side. This tool data layer is connected directly to all of our equipment and feeds all our data into the cloud. This particular data then is available at Wafer Complete, and then it's consumed into our inference pipeline. It is very tightly coupled to the training pipeline artifacts so that we know the payloads, the available models, and those enriched payloads once they become available. The inference is then conducted, and results are all stored, and then the events are sent back to the factory database for action on any of the processes or tools that are required. So just a wee bit more on the detail of how we actually constructed this type of solution. On the configuration management side, the cost of ownership has been significantly lowered on the engineer as opposed to managing all the configurations. They now manage the configuration of sensors, in particular types of sensors that we have, you know, constant, steady state, shape sensors and ones that are potentially critical, less critical, things like that. And then the criteria, along with the historical database, these 3 databases completely automate the management of those 17 million parameters within our domain. The configurations of our models then change state depending on the state within the factory and then the human selection. And then those are stored in a model artifact store, again, for the inference pipeline. A key thing about our inference pipeline to try and save cost, although it is a replicated microservice in Kubernetes, the payloads are consumed through RabbitMQ. They're enriched by a microservice again, and then the serving again is another dedicated microservice to try and scale each one depending on the receptiveness of the payloads or the time of inference. We inference on CPU, but we train on a GPU. The models themselves train faster on a GPU, they inference on a CPU, and then the results database is in Postgres, and the factory control system is a secondary system that we can communicate again with the RabbitMQ externally. So that's the decisions we made there. So now you've got your model. The model can extend, it's scalable. You've got a vehicle through the MLOps workflow to train the models, to store the artifacts, and now you've got a way to inference those. One key challenge we then found out as we were scaling this system is our data quality and integrity. You know, from our perspective, the integrity is, are we collecting the data we should be? The quality is, how good is the data that we just collected? And at the start, we assumed that we'd done a far better job than we did in this space. You know, that we had to have a strategy where we really engaged and established standards within that space. And then we monitor that real time. You know, the lesson in this particular slide here, lesson 3, is trust but verify. Already a few people have said that, specifically around e-security, but from our perspective on the data side, we can't assume that the data we have is of good shape. So our strategy is to define the standards, monitor the data real time in parallel to other systems, so it's agnostic in its performance, and then a cross-functional working group with accountability. Accountability is key here. Data quality and integrity is a gray area in your organizations because your engineers are responsible for the equipment that generate the tools. The data scientists or ML engineers would like to use the data in a good state. IT organizations store it, data engineers store it, but who then checks its validity or its integrity throughout time? Okay, so now we've got good data, we've hosted our models. The next lesson here is Schrodinger's Kubernetes service. So as I said, you know, we're pretty novice at the start of this project, just about 2 years ago. And as we started to scale this, we had a very lean team. You're talking 2-3 people most of the time doing most of this work. But don't assume that your services are running as expected or you'll be able to troubleshoot in the future. Start with the end in mind, and that we use multiple tools to try and detect the resources within our cluster, forward all the logs from the actual services they're running in a certain structure, have a log troubleshooting solution that actually allows you to go through all the historical inferences and executions or even invocations of your functions, and then alerting on top of that so you know first before your customer tells you that you have a problem. Customer in our case being within the engineering business. So again, Schrodinger's Kubernetes service, do not expect it to be there. You need to check first. So now that you've got your system, it's got your models, it's available for inference, scale the model, you've got good performance, but essentially you've just got something that's generated electricity use in your data center. What you really need here is firm engagement with your engineering teams and collecting their feedback regularly. A few presentations have said this already. Clear adoption strategy and the engagement with them. So the lesson 5 here is the human in the loop is not a bug, it's a feature, right? So the human aspect of the system and how it's being used and applied, and then selfishly, from a Gen AI perspective, this validation database that we're talking about here, you know, we've got the serving pipeline and we've got our results database, and other solutions can start to use the results from this database, but the validation from humans attaches the algorithmic output to the actual tacit knowledge of the engineer. So from our perspective, in the next generation of our AI models, as I said, the Gen AI models can't scale to these million parameters. It's just not practical at the moment. It's a bit terrifying at the speed that some of that stuff's moving, but what we are doing at the moment is building up a good tacit database of all the alerts and the associated engineering feedback so we can use them later, and very much empowering the engineer with a series of reports or interrogations so that we can let them see exactly what the system's doing at any given time. We don't want to be custodians of the particular system. We need to democratize that capability so that they are self-service. So, results and case study. So we're plenty of time left. We're going to catch up here. So this It's a very noisy slide, but I couldn't get it any way to try and describe the connectivity of an actual example and then some of the output. So we're just going to start and go around it very slowly. The top, you can see some distributions, hopefully, of data at the bottom. This is the output of your reconstruction error from your convolutional autoencoder. Very simple algorithm. This score now changes. So you imagine a million parameters that engineers are tracking. This score will change. It will break a predetermined threshold or dynamic threshold, and then there's a review from the engineer. At the current piece of our roadmap, we are still relying on engineers to engage the system, and from there provide us the feedback and intuition to actually take action in the factory. At the moment, the engineer has a fully connected application space within this, say, front end, right? So there's like an overview front end from a modeling perspective. They can then validate using factory context from other systems what the current status of the factory is, what are the other key data points telling them, and then from here you can look at, first of all, the model scores, then aggregate response variables, then raw trace examples of the actual tools as they run in production, and then compare good and bad runs. And then from here, you can then look at within aggregate of the trace, and then a Pareto of the scores in comparison to all these data sources. So you can see the efficient thread that we're trying to drive engineers, lower that inertia that's required in order to get them to engage the system. In this example, the sensor was found to be not reading, and there was a chuck bias issue, and there was a metal flake causing a shortening on the chamber itself. So there's a practical physical manifestation of this particular score the whole way through the resolution. And as you can see here very neatly, almost one that we canned earlier, the solution was resolved and the data distribution appears back to where it should be. So there's a validation in the post loop. Key challenge here, very human-centric, and although historically we would have relied on the engineers to investigate, potentially too late in these data sources here, we can now be more proactive and get them to drive to an event much earlier and then interact with the process to not expose our supply chain to more defective product. So some deployment statistics for the entire system, and then we're going to wrap up with lessons learned and reflect on what's next. So current deployment, this project is about 24 months in duration. Slightly before that, I was working part-time as a PhD researcher to work on the algorithms and then how do you scale those and what the performance is when you change some of the factory parameters. At the current deployment, we are about 30% of our wafer factory. The challenge with this number is that we originally had so many tools connected into that data sphere, and as more tools come online and then we can see the realized value, that number, which is the total, keeps increasing. So it's a significant scope creep. But it's a victim of our own success, and that's good. Within this space at the moment, on that 30% of deployment, there's over 5,000 trained models, and that accounts for millions of parameters at any given time. We currently process 1,600 payloads per day, and I'd say 500 million samples. 1,600 payloads per hour with 500 million samples per day to go through. On average, a model is inferenced between 1.3 seconds, and then the total pipeline, so model inference, getting the model from memory on demand with the payload making the inference is about 1.3 seconds. The total pipeline from our on-premise instance in the factory into the cloud, returning back to the factory with a decision is around 60 seconds. Our latency is more than met in this in other industries like finance and stuff. They may need much more latency. That's much more satisfactory for us. And of those 5,000 models, on average, it takes around 4 minutes to train each one. So these are pragmatic numbers that you can expect in this type of system. So lessons learned. Let's summarize what we've learned so far from our perspective. And as I say, the challenge to you in the crowd, if you have any questions, is was this a good idea, or should we have took a shortcut somewhere else and saved ourselves the time? We'll reflect on the Gen A impact in a second. But poacher turned gatekeeper, your subject domain expert, the engineer, needs to be involved. He or she can inform things that you don't even know goes on in that hidden factory. If you don't work in a factory, then you're hidden both business process or you're hidden customer process. And that's key to starting with the end in mind and having a successful arc. Faster horses, Mr. Ford. We can't anchor ourselves to what we know in the factory. We had to go outside the factory, try to experiment and improve that over time, much like Mr. Ford and the Model T, for those that don't know the reference. Trust but verify, the Russian proverb, build trust in the system and the AI, but we need to verify that and have rigorous validation and verification processes. And then Schrodinger's Kubernetes service, essentially going back to Schrodinger's cat of is it dead or alive, until you open the box you don't know. You need to know what's on that Kubernetes service. In particular, coming from a data science background, the whole MLOps space is very complex and at times difficult to maintain given a lean team. And then finally, the human in the loop is a bug. It's not a bug. As a Freudian slip. The human in the loop is not a bug, it's a feature. And that feature is to keep them constantly improving the system over time. And ultimately, within the GenAI space, we need their tacit knowledge to improve our algorithms into the future. So you're probably thinking, you're at AICon, everybody's talked about GenAI, and this is an old model that's a couple of years old. It's pretty vanilla. So what we're currently working on over the last few months is trying to move into that space. And for me, it's a bit of an existential crisis, because some of the models that we worked on and the ecosystems and things like just previous presentation, 2.5 minutes, and then you're questioning, did I do anything wrong for the last 2 years, and will I have a job next year? But what we're seeing at the moment is the workflow that I talked you through, where you've got an AI system so AI from the perspective of traditional AI, it's deep learning and things like that. That can scan the metadata and provide further context to your generative AI model. So now you've got a pillar of there's something analyzing all your sensors. The next part is, you've got other types of systems, and through decades of innovation, integration, automation, we've got all these silos all over the factory. So you've got equipment maintenance history, you've got key output variables, you've got the maintenance, the technicians logging all their jobs, you've got all these types of information, you've got unstructured data and documents that you tell everyone, right, these are the steps you need to follow in a troubleshooting step. So at the minute, we're very isolated, and we've only got the sensor data and what you should do after that. But what we're working on is, how do you stop funneling all this information into the human intelligence? So this particular bottleneck that we're encountering now with some of these systems, even though we've been able to minimize the space and the number of alerts, that alert fatigue or the repetition of some alerts where it could be automated, there's an opportunity there. So the human capacity to consume has been saturated from our perspective. And what we're working on here is like a GenAI fabric that connects those different data sources. So from the proper terms, it's there's a potential RAG on the unstructured data, and then MCP access through tools to the other types of data sets. And what we have is a way to circumvent that human bottleneck and automate some of our tasks. And on our early tests, there is an opportunity to do that. However, from the perspective of previous presentations, what is the repeatability, reproducibility of that? And if our system currently says you should run a different process and it completely destroys a product that's worth a significant amount of money, then that's a responsibility that we have to account for. So that's our next phase. That's all I have. So I just have to thank you for your attention, and any questions. We're well ahead of time here, so no.